Hey guys, hope you're doing well. I'm just gonna check my audio settings. I need to make sure that I'm good here. So we should be good now. I just needed to check something. So we're into our last part of the um, the discussions about common ion. So in common ion, the last thing we're going to talk about is gravimetric analysis. So I'm going to share my screen and then we're going to talk a little bit about gravimetric analysis. Now, we talked a little bit about fractional precipitation last time. And we talked about the fact that if the KSP values are different, we can selectively choose to pull out one or more of those ions by manipulating what we add to get that out. Gravimetric analysis is a way that we can typically do that without, sorry, I was driving myself crazy, that we can typically do that without much of an issue. So it gives us a flowchart of how we would add certain things to this to precipitate different cations. So here we're looking at cations. We're trying to get out cations of group 1 metals, then group 2 metals, then group 3 metals, and then group 4 metals. So if we have a mixture of those things that we need to look at, that's what we're trying to do here, okay? And so what we can do is look at this and say, okay, if I have different metals, how would I get them out? And that's what this is about. So what you can see from this is if I have all of them in there and I add HCl, I'm going to precipitate the group 1 metals first. And that includes Ag, even though it's not a group 1 metal. Ag is in there, mercury 2, it's Hg22 plus is in there, and lead is in there as well. So those will come out. We can then add, and it's after that, H2S will get us our group 2 precipitates, and copper sulfide, cadmium sulfide, mercury sulfide, and that's mercury 2, tin 2 sulfide, and bismuth sulfide. Okay? We can then change that from an H2S, which is an acidic solution, and make it basic. When we make it basic, we can then drop out our group 3 precipitates. So COS, FES, MNS, NIS, CNS, ALOH3, and CrOH3. Okay. And if we then filter all of that off and add Na2CO3, that'll give me BaCO3, CaCO3, and SrCO3. Now, if we want to precipitate just one of those things, we have to be careful about how we do it. And of course, if we get them all out in one group, then there are ways that we can try and separate them after the fact. Okay? What you'll find is that sodium, potassium, NH4, those always stay in solution because they're always soluble. So solubility rule 1 states that they're always soluble, so we can't get those out this way. We have to do it through something else. Okay? So that's the discussion about what gravimetric analysis is. This is actually a technique that's used in industry to try and remove cations from wastewater and things like that. So it is a way that we try to do these kinds of analyses. Okay, and I mean, we may analyze them, we may not. We may just be trying to get them out of there. So that's one thing. Now let's try this again. We're going to do some application of this so that you'll see how you might see this on a test. So if I have a solution of silver, tin, chromium, and barium, what would I have to add and in what order to separate these metals? What salts would I form? Okay, so I have silver, Ag+, tin is Sn, and I think that's a 2+, but I'm not sure. And I'll explain how I find out. Cr, and then Ba. So those are the things that I'm trying to precipitate. So I'm going to look over here, and I'm going to see, okay, silver's right there. So here's where my silver is. I see Sn right here in this box. I see the chromium hydroxide here, so the Cr, and then that Ba is down here. Well, isn't that fancy? So if I take this mixture and I add HCl, so I take the mix, I add HCl, I get out AgCl. Cool, awesome. If I then add H2S, I get out an SNS, and it's an SNS. That's what it says in the thing, which means that tin is a +2, and sulfur is a -2. Okay, awesome. Now I can add NaOH. And when I add NaOH, then I precipitate the CrOH3 and filter that off. And then we can add Na2CO3 and get out of that the BaCO3. So that's the order I would have to add those things. And trust me, we always add them in that order. That's always the order that we add them. I'm just asking you so I can make sure that you know that. Okay. We add them in that order. Those are the solids that precipitate at each level and what they come out, the solids that they are when they precipitate. Okay, that's awesome. So let's take another look. Can we use this again? So now I have a solution of copper, Cu, cobalt, lead, and zinc. Okay, fine. So I see lead, Pb is here. I am looking for copper, Cu is here. I am looking for zinc, Zn is here. And that leaves me with cobalt, Co, and actually Co is here as well. So now I've identified where all of these metals would come out. The first thing is to add the HCl. That's going to precipitate the PbCl2. That's awesome. We then add that H2S, and that's going to give me the CuS. But then if I add NaOH to that, I will precipitate both the ZnS and the COS. And so we will have to do something else or be very, very careful how we do that to see how we can get those separate. And we may be able to use fractional precipitation, in which case we add very slowly in a very controlled fashion to be able to get those apart. But we're going to have to do a little more work here. It's not as easy as it was the last time. Okay, awesome. One more time. I want to see if I can separate mercury 1, and mercury is weird. It always appears as Hg2, but if it's a 2 plus and a 2, then that's mercury 1. Mercury 2, which is Hg2 plus, barium, Ba, and calcium, Ca. Okay, fine. So I look at my list over here. I see Hg2Cl2. So Hg2Cl2 is this Hg2 plus the 2. So that one's over there. If I look down, I see the HgS, and that's the Hg2 plus. So that's that one. I find barium, and it's down here. The barium is right there. And that is actually a 2 plus as well. And of course, the calcium is also here. Okay. So what that means is that I'm going to have to add the HCl. When I do that, I precipitate the Hg2Cl2. I add the H2S. That precipitates the HgCl2. And then I still have to add the NaOH. It's a pH thing. So if we don't have the right pH, this is not going to work. So we need to make sure that we've added that hydroxide and we've got that pH where it needs to be so that we can then precipitate the next stuff. Now nothing comes out here. And I then have to add that Na2CO3, and that will give me the BaCO3 and the CaCO3. And again, I'm going to have to be careful how I manage that. So I may be able to fractionally precipitate to get one of them. I may just precipitate them all out. It depends on what I'm trying to do, how I will handle that. But that is where I would get them. Okay, awesome. And that's everything for that. Now, questions, comments, problems? Hopefully not. But I do have some sample questions that I want to talk about. So this is the last thing that we're going to talk about in this section. We're going to go ahead and add a note page to this. And then I'm going to pull up the slides on my computer so I can look at them. I am still referring to the slide from your slide deck. So those questions are on that slide deck. And this is this one. Sorry, too many presentations. So my sample questions. It says calculate the concentration of aluminum ion in a 0.025 molar AlOH3 solution where the pH equals 8.4 if the KSP equals 1.8 times 10 to the negative 33rd. Okay, I have information. Awesome. Where do I start with that information? I'm looking at the solubility of the aluminum. I want to know how soluble that Al3 plus is. So that implies to me that I need to be talking about this AlOH3 solid coming apart to give me that Al3 plus. I need to be able to look at that. I also know that when I do that, I get 3OH minus. And of course, that's an R. I have an initial concentration of 0.025 that goes there, but that's a solid, so I actually don't care about that. It doesn't matter at all. I can actually do that. I know that when one of those comes apart, I get plus X on the Al3 plus, and I get plus 3X on the 3OH minus. We assume that both of these are 0 to start. And that means that at equilibrium, my concentration of Al3 plus will be X. My concentration of the 3OH minus is going to be 3X. But is that everything that I know and that I have? And the answer to that is no. So I would initially write this and I go, oh crap, I forgot something. What did I forget? I forgot that they told me that the pH is 8.4. So if I wanted to, I could calculate pOH, and I actually need to, 14 minus 8.4, and that should give me a number if I grab a calculator, 14 minus 8.4, and it gives me 5.6. Okay, so that's my pOH. If I take 10 to the negative pOH, that's going to be my OH minus. So I take second 10x negative second answer, and that gives me 2.5 times 10 to the minus 6. So this concentration right here is not 0. It's 2.5 times 10 to the minus 6. And we can, so when we get down to the equilibrium, this technically speaking should be 2.5 times 10 to the minus 6 plus 3x. We're going to ignore the 3x because we need to do that to be able to do this math. Okay. So when I set this up, I know that my KSP is equal to that Al3 plus times the OH minus cubed. I know my Al3 plus is an X. My OH minus is 2.5 times 10 to the minus 6, and that has to be cubed. Now, I got a question from a student about why are some of them brackets and why are some of them parentheses. The brackets indicate that we're talking about a molar concentration for something. That has a specific meaning. When I plug values into that, I do not, so instead of having that concentration there, when I plug any value in, be it an X, be it an actual concentration, I use parentheses to indicate that that's the value that goes there. And I sometimes include them everywhere, sometimes don't. Okay. That's just so that I can keep track of, I have 1, I have 2, did I get all my numbers where I'm supposed to get them? Okay. Now this KSP is 1.8 times 10 to the negative 33rd. So if I want X by itself, that's going to be 1.8 times 10 to the negative 33rd divided by 2.5 times 10 to the negative 6th cubed. So let's do that happy math. 1.8 second EE negative 33 divided by 2.5 second EE to the negative 6, and then that is raised to the third power. And that gives me 1.15 times 10 to the minus 16th. Okay, that's my concentration of Al3 plus. And that's what they were asking me for. It says calculate the concentration of the aluminum ion. So I'm done. I have done exactly what I needed to do. Okay? So that's how I approach that. Let's talk about our next problem. So the next one says, calculate the concentration of phosphate ion. So PO4 3 minus, it's a concentration, so I'm going to bracket that. In a 0.036 molar Ca3PO4, and that should be at 2, it should be Ca3PO4 2 solution where 12.26 milligrams of calcium nitrate, CaNO3 2, are added if the KSP equals 1.2 times 10 to the minus 26. Okay, fine. Just taking a moment. I know that this KSP is for Ca3PO4 2. So that's going to be equal to the concentration of Ca2 plus cubed times the PO4 3 minus squared. So that's what I'm going to be plugging into eventually. I need to make a rice table because I can't keep track of all of this stuff if I don't. And that Ca3PO4 2 solid becomes 3 Ca2 plus 2 PO4 2 minus. Right. So that's my R. My initial concentration of the of Ca3PO4 is 0.036, but that's a solid, so I don't care. I put it in there, so I want to accommodate every piece of information that I've written down. I want it to go somewhere. If I put it in there and I realize I don't need it, then I can cross it out. That's fine, but I've at least done something with it, so I know I don't. Okay. Now, the other thing that they tell me is that 12.26 milligrams of CaNO3 2 have been dissolved. Okay, let me ask you this. So that CaNO3 2, what happens to that? Well, it's an ionic compound, right? It's a Ca2 plus and NO3 minus. Since it's a nitrate, it's completely soluble. So that means that this is going to come apart to give me a Ca2 plus 2 NO3 minus. And whatever this concentration is, that's going to be over here. But I don't know what that concentration is yet, do I? No, I don't. All I have is a mass. So I know that I have 12.26 milligrams of the CaNO3 2. I know that there are 1,000 milligrams per gram. And then, of course, it's grams of CaNO3 2. So that'll cancel my milligrams and I'll be in grams. If I want to get rid of those grams, I need to divide by the molecular weight. So I can find my cheat sheet, my happy little calculator. CaNO3 2. And I can see that that has a molecular weight of 164.09 grams per mole of CaNO3 2. Okay, that's awesome. Now, did they tell me the volume of this solution? They didn't. So technically speaking, I don't have enough information to do this, but I can make an assumption. So I can assume this is 1 liter. So if I make that assumption, then that tells me what that molar concentration is. Now, if it isn't, and somebody should have given me a value for that, then it would be a different value. But nobody told me. So that's the assumption that I make. And I feel justified in doing that because I don't care what your answer is. I care that you know what to do with this math. So if I was supposed to give you a volume and I didn't, then showing me what you would do if you had a volume is beneficial. So that's my thought process in saying that to you. So I take my 12.26, I divide that by 1,000. I then divide by 164.9, and that gives me 7.47 times 10 to the minus fifth. And that's equal to the CaNO3 concentration. But what's the common ion out of these? It's a Ca2+, right? And so that concentration of Ca2+ is exactly that same value, okay? Because there's only one Ca on that CaNO3 too. So I plug that in here, 7.47 times 10 to the minus fifth. Okay, my phosphate's going to be 0 because I haven't broken any of this down yet. When I break them down, I'm going to get 3x here plus 2x there. And that's based on the stoichiometry. So the numbers up in that equation apply to those x's. At equilibrium, this value right here is going to be 7.47 times 10 to the minus fifth plus 3x. We ignore the x. And this is going to be a 2x. Okay, so again, we're always assuming that that additive x is going to be small comparative to what we already have. And so I can take those values and I can plug them in up here. 7.47 times 10 to the minus fifth. That is cubed. And then I have my 2x, and that is squared. Now, do I know that I have to cube that? Absolutely, because that's what my equation says I have to do. And that equation says that because of the stoichiometry. Okay, so they're all related. So if I've done everything in the way that I should have done it, i.e. I write my KSP the way that I need to, then I know that this particular concentration needs to be cubed. Okay, fine. So I take my 1.2, second x, negative 26. I'm going to divide that by 7.47 to the negative fifth cubed. And so my 2x squared, and it's 2x, the whole thing ends being 4x squared, is equal to 3.83 times 10 to the minus 14th. I divide that by 4. That leaves me with an x squared is equal to 9.59 times 10 to the negative 15th. I then take the square root of that number, and that gives me that x is equal to 9.79 times 10 to the minus 8th, which is very small compared to that 7.47 times 10 to the minus 8th, okay? So if I need to know what that phosphate concentration is, which is what they asked me for in the beginning, that's what I wrote right there, then I need to take that number and multiply by 2. And I know that because it says 2x right here. So that answer is 1.95, and it's actually 1.96 because I have to round it, times 10 to the negative 7th. And that is the concentration that I need to report as the concentration of phosphate. Okay, so that's what I need there. Awesome. That was fun. Let's try another one. If I add 12.64 milliliters of 0.026 molar sodium hydroxide to a 50 milliliter solution of magnesium nitrate, and Mg is a 2+, so it's an Mg NO3 2, because NO3 is -1. What is the concentration of magnesium nitrate in solution? Okay, that's awesome. Now, magnesium nitrate, let's take a look at that. Is that a soluble salt or an insoluble salt? It's soluble, okay? And I know it's soluble because it's a nitrate. So all nitrates are soluble, which means that the MgNO3 completely dissociates to give me an Mg2 plus 2 NO3 minus. Awesome. The NaOH does not appear anywhere in there. So it has nothing to do with that, right? So I have a 50 milliliter solution of this. I have no idea what its concentration is. So I can't figure out what that concentration is. Okay. But I know that whatever this concentration is, this will be the same. Okay. Now, I realize that that's a little tomfoolery because I'm asking you a question where you think that you're going to need to solve this insoluble solid and yada, 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 but we need to recognize that the question that I've been asked may have information in it that I need to think about that's outside of what we thought it might be. Okay, so there's no context given to these questions on the test. So make sure that you're answering the question that was asked and considering everything about that solution as you do it. Okay, so that's everything I have to say about this particular topic. Questions, comments, problems, concerns, anything. If you have them, please let me know. I'm going to go ahead and get this posted. I will be doing the redox lecture tonight, so I will post that for you. This is everything that you need for the test. So if you have questions, let me know. There is, oh, and I need to show you that. Sorry. Let me do this. In the shell, and let me make sure. Sorry, not sure it's the right shell. They should be in the same order, but not everything is. So if I look at that and I go into content, when we're in content, exam 1, down here is exam 1 practice and the answers. So here are the questions, here are the things with the answers. Now you'll find the answers interspersed through here. So we have lots of hen scratching. I do know that there is one problem. I got an email from a student when I was working on this, and the math that I did for number 15 is wrong. My calculator hates me. So number 15, where is it? It's down here somewhere, I swear. So this urea one, we know that this concentration is 0.001. The Kb for urea is 1.5 times 10 to the minus 14th. So this should not be 1.5 times 10 to the minus 8th. Okay, so that calculation is incorrect. So you'll need to make note of that at that point. It should be 1.5 times 10 to the minus 17th, I believe is what I get when I do that. 1.5 negative 14 times 0.001, which is 1.5 times 10 to the minus 17th. And then I take the square root of that value, and that gives me 3.9 times 10 to the minus 9th. Okay, so that is the concentration that should be reported there. Okay, I apologize for that. I'm very sorry. I hate it when I make mistakes when I'm doing it, but my calculator hates me sometimes, which is why I often talk through working on my calculator. So there is the stuff for the test. I will get this posted as soon as I can. You'll start to see things populate for exam 2 in here. I'm hoping that will all go up this weekend. And like I said, the redox lecture will be recorded today. I'm going to try and record the voltaic cells reaction rates and rate constants this weekend so that you have all 3 of them available. And then we'll have one more for mechanisms that will be sometime soon. Okay. So that's everything. I'm going to go ahead and stop sharing, and then I'm going to stop recording, and I will see you guys soon. Thanks.